Now for this example, I want to do more than just the simple labels up here. I want to actually talk about like a redox reaction, acid-base reactions, and how to identify those as well. First off, let's just use 1, 2, 3, 4 for synthesis, decomposition, single displacement, double displacement reaction. First off, synthesis reactions, that would be when two or more things come together to produce something new, so that's a synthesis reaction. Decomposition is the reverse, okay, so a lot of times, well, heating or electric current, sure, to destroy something, take it to its elemental forms oftentimes. That's a decomposition reaction. A single displacement reaction is this guy here, where one element, usually a metal, reacts with some compound here, and it kind of breaks this one apart, and the one metal sort of squeezes in and replaces a single element in the other reactant. And you see that there's that aluminum there, and one thing got kicked out. And then the double replacement, well, that's where you have this kind of like one, and it's usually a set of salts. That's really common. You can see an acid-base in neutralization reactions. These are two salts, and so the cation here will pair up with the anion there to produce one of the compounds, and kind of vice versa. The cation of the other pairs up with the anion of the other to form a new compound. So this is our double displacement reaction there. Okay, fine. These are very general terms. Let's use a little bit more specific terms here. And there's examples of most of them that we want to deal with. First off, let's just talk about redox. So this is in no particular order. The primary feature of redox reactions is that there's some kind of electron transfer. Now, we don't necessarily break that down into too much detail. What we're looking for is a change in the charge of at least just one atom in the formula. And you don't have to analyze every single atom. You're just looking for that one feature in one atom. And let me just go ahead and there's actually 3 up here. All of these are redox reactions. And let's just sort of map out, how do I know that? Well, I said I'm looking for a change in the charge. Well, how does aluminum metal get to this salt formula? Well, it's doing something like this. Actually, it's going to lose electrons here. Right. What is that charge in that salt formula? It's a +3 charge. This is why we do like nomenclature before we do this kind of topic. Through nomenclature, you not only learn how to name the compounds, but you also learn how to break apart a compound and know what charge you're looking at there. How do I know 3 electrons got lost? Well, because that's just what happens when something has a +3 charge. If that's the change that you see here, that is due to the loss of 3 electrons. Right? It's only the electrons that are going to move around on a molecule. Protons don't change. Aluminum is aluminum. B, what am I looking at? I'm looking at potassium, and potassium there, yes, but on the reactant side it's a potassium metal, and on the product side it is a potassium salt. There's that electron being kicked off. In D, it's the opposite, okay? Charge on that copper, this is a salt, so the copper is a +2 state, and I'm going to the elemental form. An elemental form that has a balance of protons and electrons, giving rise to a total neutral charge on it. That's just Cu. Now again, in each one of these, I just picked out one element to talk about, and it just happened to be the loss of electrons here and the gain of electron here. But just sort of wrap this up, there is an electron transfer taking place. Like for example, the 3 electrons that the aluminum loses here are actually gained by the hydrogen to form the hydrogen gas. Now we're not going to break down reactions in that kind of detail, so I'm not going to worry about drawing it here. But just know that in all of these redox reactions, there's a transfer of electrons back and forth between individual reactants here to cause the chemical change that we were looking at. Last thing, redox stands for reduction and oxidation. So if it's loss of electron, it is oxidation. And then if it is gain of electron, it is reduction. A mnemonic that you often hear with this is Leo, the lion, goes grr, for what it's worth. Another type of specific reaction that we saw in this chapter is called a precipitation reaction. And honestly, the thing to know here is that you go from a set of aqueous solutions to at least one thing that is a solid. And I want to mention B is the only precipitation reaction here. Aqueous, aqueous going to that solid. Yes, there's a solid forming here. Yes, there's a solid forming here, but it's not coming from like two aqueous solutions coming together. For this class, and honestly, most of the examples I can think of, precipitation reaction is really going to be looking like one of those double replacement reactions. And the last thing I'll comment about a precipitation reaction is that the salt that doesn't react, that's associated with what we call the spectator ions. Long story short, potassium doesn't actually change. Sulfate doesn't actually change. It pairs up with a different partner, but over here potassium's free-floating ion, here potassium is a free-floating ion. The chemical reaction is associated with a solid that's formed. Potassium and sulfate are just watching the reaction takes place. They are spectators in the reaction, if you will. The last type of specific reaction that I just want to mention here is called an acid-base reaction. There's not one here. We'll take a look at one in a second. But with an acid-base reaction, well, the main feature here is that you have a H+ transfer. This is actually a proton being transferred. I said down here that protons don't change in a reaction. That is true. This is a hydrogen nucleus, a hydrogen transferring from hydrogen cation from one compound to the next. The main feature that you're looking for here is going to be an acid plus a hydroxide salt. Now, there's a lot more I could say about an acid-base reaction, but for our class, that's what you're looking for, okay? This topic occupies like a month worth of material or more in like the second Gen Chem. For us, it's really just recognizing that a particular reaction is an acid-base reaction. And let's just take a quick look at one of those. So here's our acid-base reaction, and it is sometimes referred to as a neutralization reaction. Basically, you're taking something that is acidic, neutralizing it with a base, or vice versa, however you want to say it, and then you form water, which is pH neutral. End of the semester, we'll learn more about pH scales. That's not our concern right now. But again, how do you recognize this? An acid plus an hydroxide salt. Notice hydroxide. This is going to be the base in all of our acid-base reactions. So what's the common feature for a base? Hydroxide. What's the common feature for the acid? Well, the common feature for the acid is a hydrogen on the left-hand side. That's what you're looking for. That tells us really how many protons can be transferred in a given reaction. And this arrow here is trying to get at the idea that a proton is being transferred. Again, there's more you can say about this, but for our class, that's enough, okay?